We just met the map and the MMSE for SparseLand signals, and they are both impossible to use in practice. We now discuss approximations of them. Suppose that we know that the cardinality of the solution is 1, that is, S has only one element. In this case, if we return to the posterior expression of P of S given Z, we could simplify it dramatically, since ds has now only one atom, and thus Qs is a scalar, and so is h of S. The rightmost term in the above expression is a constant and thus can be omitted. After a little bit of algebra, we get this lovely expression. It describes the probability of each of the atoms to be on our support. Let's suggest a map and MMSE for this case. In terms of map, we should simply compute all the m values, one per each atom, and choose the one that maximizes the probability. Well, this is exactly what OMP would have done in its first step, since these values we are looking at are simply related to the inner product of Z by the atoms. What about the MMSE? We should do as above and compute all the probabilities and then draw at random an atom from this distribution. Repeating these many times and averaging is the MMSE estimate. This is very similar to what the random OMP does in the first step. In fact, please go back to the description of the random OMP and you will see that these probabilities are exactly what we suggested, and now we even know what constant C to use. All the above referred to the case where S is known to be 1. If S is bigger, then these are still valid first steps in the approximation algorithm. More specifically, suppose that we employ a greedy algorithm that gradually sweeps through growing supports. We have accumulated so far the location of k-1 non-zeros, and now we are wondering whom should join as the kth. One option in front of us is to evaluate this complete expression for all the possibilities of choosing this kth element while fixing the k-1 earlier ones. Then we could either take the maximum if we are after the map approximation, or randomly draw the next atom if MMSE is what we are after. This is a reasonable algorithm, but we would like to suggest something slightly cruder. Compute the residual and repeat the process of the first step that we described. The benefit is that these probabilities are easier to evaluate. Now think about it. This is exactly what OMP and random OMP are doing. Here is a short demo of the various methods discussed. We present the ratio of the resulting estimation MSE divided by the input noise as a function of the level of the noise in the signal. In order to be able to evaluate exact MMSE and map, we chose M to be 16, and this way we can sweep through all possible supports. Here are the parameters of the experiment. An element can be non-zero in alpha with a probability 0.1 and then drawn from a normalized Gaussian distribution. We will run the random OMP 50 times and average, and all the experiments are run 1000 times and averaged. This is the performance of the oracle. These are the MMSE and the map exact estimators. This is the OMP which aims to approximate the map, and here is the random OMP which targets an approximation of the MMSE. Of all these, the oracle is impossible to get in true problems because we do not really know the support. Similarly, the exact MMSE and map are impossible to get due to the computational limitations. Thus, we are left with the OMP and its randomized version. What happens in the unitary case? Recall that in the P0 epsilon, we managed to get a closed form expression for the exact solution in this case. Well, something similar happens here. Without exposing the fine details, we can say that both MMSE and map have closed form exact estimates, so we do not need approximations. The map gives a shrinkage curve that looks like this. It resembles the hard thresholding, but it is slightly different. The MMSE estimation has this expression as its ideal estimation, and it looks like this. Observe that the shrinkage curve is smooth and touches the zero only for the zero input, resulting in a representation that is not sparse. Nevertheless, small entries are damped as before. And now, here is a demo to show the oracle, the MMSE, and the map estimation under a unitary dictionary. As opposed to the previous demo, now we can use higher dimensions, since we have access to the exact MMSE and map estimators with no need for approximations. In this experiment, we assume a dictionary of size 100 by 100 entries. We did not discuss it here, but we also have closed-form expressions for the errors these estimations provide. In the graph shown, we present the oracle, the MMSE, and the map, and each of them is evaluated in two very different ways: by empirically testing these estimators and averaging the results over 5,000 experiments, or by using the formula we have. As you can see, there is a perfect alignment between theory and practice. We can also see how the oracle is the best of the three and how the MMSE is better than the map.